This video is going to discuss partial derivatives and only give an introduction to them, as they are their own beast in of themselves. So just to kind of set the stage here, what we are going to do is start to shift our focus on a function and start to look at functions that are dependent on multiple variables. So you might have many different inputs, okay, into a function. So normally we only talked about f of x, g of y, okay. Now we're going to say a function is f of x and y, okay. So it's a function where we have multiple inputs, and for simplicity I think we're only going to focus on two inputs, and there's a single output. So there's two things put into the function, one thing is put out, or is resulting from that, okay. In reality, I've seen functions with as many as 16 variables, okay. So, and this is actually how functions operate in real life, is you often have many factors influencing your outcome, okay. So if we want to look at these types of functions, we can still find derivatives. We can differentiate to our heart's desire. The only thing is, though, that partial derivatives are just that, in that we can only look at part of the change, okay. So we can only look at how fast the output is changing with respect to a single input. There exist other methods where you can look at the entire change, but that's going to be outside of this course. So what we want to do is think, okay, what is the rate of change in z as, say, x changes, okay? And when we do this, when we look at just one variable, how it changes with respect to one variable, the other variable, we think of it as constant, okay? So we think of it as not changing, as it's a fixed value, okay? And so we get a partial derivative out of all of this, and then the notation that we use is, it looks like a squiggly d, okay? So the partial derivative of z with respect to x is denoted by this symbol. I call it del, D-E-L. Okay, so I would say that this is del and then z over del x. That's what I've heard. There might exist other notation or other language for this, and then so you can either say del z, del x, and that would be Leibniz notation. There is no real prime notation equivalent, but what we often write is f with a subscript of x, and the subscript is denoting which partial derivative we're looking at, okay. So again, just to reiterate, del z over del x is equal to f sub x of x and y. And again here, if we're looking at the rate of change with respect to x, y is constant, okay. We'll go through some more examples with all this, okay. And then similarly, if we're looking at the partial derivative of y, or of z with respect to y, it would be del z del y is equal to f sub y of xy. And again here, since we're looking at y, x would be treated as a constant. And then just a note on interpretations, because we love to ask you about interpretations, what this all means. So del z del x, that would be the instantaneous rate of change in z, so it's still the change in z, due to the change in x. Okay, so as x changes. Similarly with y, it's just change in y. Okay, so we're still looking at the rate of change in the overall function, just with respect to one variable only. Okay, so now let's see how to find these things. Okay, so we're going to assume for the entirety of all this that we're in the domain, because that's a whole separate issue. So we're going to assume that we're in the domain, and we want to determine the partial derivatives of the function. So when I say partial derivatives, there may be one, there may be two, there may be a lot. So instead, we're just going to focus our attention on one thing at a time. So I'm going to find del z, del x. Okay. So again, just a note here. This means that y is constant. So whenever I'm differentiating and I see a term that only contains a y, that is going to drop off. Okay. So I think of y as constant. So what I'm going to do here is I'm going to write it in a little fancy way. Okay, so del z, del x, any term containing x, I'm going to have to differentiate, and then anything without x, that's just going to drop off. Okay, so y squared here, it's a y, it's constant, derivative of constant is 0, that's going to drop off, and 1 is going to drop off. Okay, so now here, I'm going to write this as 3 square root y, so I'm grouping the constants together, and then I would have to differentiate x cubed, so that's tick mark means prime, so I have yet to differentiate that, and then I have to differentiate x. Okay, when I do this, I end up getting, okay, so 3 square root y, that is just a constant, I leave it alone, times, okay, the derivative of x cubed, we know that by the power rule is just 3x squared. Okay, and then I have to subtract off the derivative of x. Derivative of x is just 1, and if I want, I can rewrite this as 9 square root y times x squared minus 1. Okay, you don't have to, I did. Okay, so now I'm going to erase this. Okay, and so I found one partial derivative. I also need to find del z, del y. Okay, so now this is the rate of change in z with respect to y, and here x is constant. So that means anything that has only x is going to drop off. So minus x, that's going to go to 0 because x is a constant, and the 1 is still going to drop off. So I end up getting del z, del y. So I'm going to, again, group this, so 3x cubed, and then I need to look at the derivative of square root y, and then also look at y squared and that derivative. Okay. Now via the chain rule for that first one, actually, well, power rule, I'm sorry, 3x cubed, derivative of square root y, I'll let you write that out, but by the power rule, 1/2 y to the minus 1/2, and then plus derivative of y squared is 2y. Okay, simplifying again, if you wish, 3/2 x cubed y to the minus 1/2 plus 2y. And at this stage, you could write it using positive exponents, using radicals. I don't really care. Okay. The important thing to me is that we got the partial derivatives right. Okay. So again, just to review, del z, del x, that means that y is constant, so any terms containing y or a constant, any terms that contain only y drop off, as well as other constants. And when I'm performing calculations, if y is adjoined to x, I just think of it as a constant. I think of it as 4. I think of it as 22. Okay, it's not going to differentiate as I would with x. Okay, I go through that. So I group the y, the square root y, because it's a constant, with the other constant 3, and then differentiated that first part. Okay, similar thing happened down here when I looked at del z, del y. Since I'm looking at the rate of change with respect to y, x is a constant, so that means that I would group the x any x's with a constant if they're multiplied or if they're adjoined to a y. Any other x's that are on their own are a constant. Derivative of constant 0. Okay. Now, let's look at another example briefly. Okay. So, I'm going to look at g of m and p. I'm only going to do one, and then I'm going to encourage you to pause the video, find the other, and then I will give the solution to the other one. Okay, so g is a function of m and p, and then this is the function for that entire thing. Okay, so now if I'm looking at del g over del m, okay, so you're going to have to find del g, del p alone. And again, I could also use g with a subscript of m. Okay, that's another notation we could use. And so now this means that I'm only looking at the rate of change in g with respect to m. So any terms that contain a p only or a constant are going to wipe. Okay, so that means this term is a constant, that's going to get deleted. That's going to differentiate to 0. Okay, so now here, this one, this is actually going to be a chain rule. So the first one, 3, derivative of sine is cosine. Rewrite the inside part, mp plus 1. Times, now, so that was the derivative of the outer, times the derivative of the inner. P is a constant here, and that's a coefficient of m, so I would have p as the derivative of the inside part, because the derivative of the inside part, the one would just differentiate to 0, and then p is a constant. Okay. Minus, I'll let you show this one, but by the power rule, this is going to be minus 1/3 m to the minus 2/3. Okay, and now this last one, remember that m is in the exponent, so this is an exponential function, and the derivative of that is 3 to the m times natural log of 3. Okay, now at this point, I encourage you to pause the video and find the partial of g with respect to p. Okay, the solution is going to be 3 cosine of mp plus 1 times m, and then minus t times p to the t minus 1 by the power rule, because p is in the base. Okay. And then, of course, we have to do application problems, because why not? And this is actually, again, we do these all in preparation for future events, so this is actually extremely applicable in the real world, because you do have functions that are dependent on multiple variables. So that's why we want to prepare you for these sorts of scenarios. So z is a function of profit. Okay, profit, and from selling blood pressure cuffs, profits depend on number of devices sold. So number of devices sold is x, and that's in hundreds. Cost of production is y in hundreds of dollars. Okay, and so it's here's a function. Find the partial derivatives. Evaluate the partial derivatives for 200 devices sold and cost for $100 for production. Interpret the evaluations in context. Okay, so the easy part here is actually going to be finding the partial derivatives, if you can believe that. So I want to find z or the partial of z with respect to x. So now here again, that means that any terms that contain y and only y are constant. So that means that this one's going to drop off, and so I get negative 5x to the 4th, and then the y is in, or x is in the exponent, so that means that this is going to be exponential function, so the derivative of that. The derivative of that is going to be y to the x times natural log of y. Okay. Now, in the case of z sub y, this is now going to be the partial of z with respect to y. So I end up getting, okay, now this is going to drop off because x would be treated as a constant. So here this is exponential, so this is going to be 3 to the y times natural log of 3 plus, and now this is a power function, so it'll be x times y to the x minus 1. Okay, so again, maybe go over that a couple times if that part was the confusing part, which is okay. And at this point, now we have to evaluate the partial derivatives. So z sub x evaluated at, now I'm going to use a coordinate pair. So I'm thinking, okay, x is the number of devices sold in hundreds, so this would just be 2. Okay, and then y is hundreds of dollars, so this would be 1. Okay, so I go ahead and plug that in. -5 times 2 to the 4th plus y to the x, so 1 to the 2nd times natural log of 1. Natural log of 1 is 0, so that all wipes out. And so I just get 2 to the 4th is 16 times -5 is -80. Okay, and I'll come back to units in a second. I want to evaluate the other one. So this would be z of y evaluated at the same point, 2, 1. Okay, and so I get 3 to the 1 times natural log of 3 plus 2 times 1 to the 2 minus 1, or 2 to the 1. So this would just be 3 natural log of 3 plus 2. Okay. Now in terms of units here, z is profit in thousands, so this would be dollars, thousands of dollars, and then with respect to x, this would be per 100, so thousands, I'll add thousands of dollars per 100 devices. Okay, so in terms of the derivative is going to have the units that, first of all, are the units of the original output divided by whatever the units are for the function, or for the variable that you're differentiating with respect to. Okay, and now this one, this would be thousands of dollars per, okay, so that was the units of z. The units of y are hundreds of dollars. Okay, now the units are always kind of tricky to figure out, and sometimes here, for example, z of y, those units don't really make sense. I might just say that's per $10 because thousands divided by 100, or 1,000 divided by 100 is 10. But I would recommend leaving it like that for right now. Okay, now for the interpretation part. So for the interpretation, I would write out that the rate of change in the, again, the number of devices sold, so that's z, with respect to the, I'm sorry, I have this backwards. The rate of change in the profit due to the number of devices sold, let's delete all this, is minus 80 thousands of dollars per 100 devices. Okay, and then again interpreting, so that would be for the blue part, and then the red part, I would interpret that as the rate of change in profit due to, this would be the cost of production, is, and then I would do 3 natural log of 3 plus 2. If you want to evaluate that, get a number, that's fine. 3 natural log of 3 plus 2 thousands of dollars per $100. Okay, so those would be the interpretations as well as the partial derivatives.